Okay, so we're going to go over some basic probability using Excel. So we'll start off with a simple roll of one dice. So roll one dice. Assuming there's nothing wrong with the dice, each of the six sides has an equal shot of coming out. The outcomes could be 1, 2, 3, 4, 5, or 6. So these numbers are just put in these Excel spots. There's no formula involved in those. To figure out the probability, assuming there's nothing wrong with the dice, we would do a formula 1 divided by the count. So we're going to take this entire range, this range right here, and we're going to count up every cell that isn't blank. So that's what the count function does. So 1 divided by count for this entire range, and we'll put dollar signs to make them absolute values so we could copy the formula. And we'll copy that same formula through this range. Okay, so assuming there's nothing wrong with the dice, each of the numbers has a 1/6 chance of happening. 16.67 is 1/6. Okay, there's a function that comes up in probability that might seem a little peculiar at first, but it's going to have use down the road. It's called the cumulative distribution function. And what that is basically for any outcome, because now the outcomes are now ordered. So it's not like just random colors on the side of the dice. They're actually ordered. 1, 2, 3, 4, 5, 6 follows an order. So if we wanted to know what is the probability that the outcome is exactly 1, it's 1/6. What's the probability that it's exactly 2? That's also 1/6. What is the probability that it's exactly 3? That's 1/6. But if you wanted to know what is the probability that it's 1 or less, that would be 1/6. If you wanted to know what is the probability that it's either 2 or less, that's really the probability that it's 2 plus the probability that it's a 1. So the formula for this is the sum of all the values to all the way back down to 0. And then if you want to know what is the probability that the dice is a 3 or less, that it's somewhere in this range, 3 or less, that would be the probability that it's somewhere either 1 or 2 or 3. We'd sum up all 3 of these. So there's a 50% chance that the value of the dice will be 3 or less, meaning 3 or 2 or 1. And then just continuing the cumulative distribution function for 4, the probability that the dice comes out 4 or less is 2/3, 66.67. The probability that it's 5 or less, meaning 5 or 4 or 3 or 2 or 1, is 83.3%. 5 out of 6 is the probability that it'll be 5 or less. The cumulative distribution function of the final number should always be 100%. Should always be 100%. The probability that you roll a dice and it comes out either 6 or less should be 100%. Has to come out something. In addition to that, the total of all the individual probabilities should also sum up to 100%. So this symbol here means the probability that the value, the big X, is the outcome of the X is a particular number, meaning this number, the outcome. The probability that the result is a 4 is 1/6. The probability that the result is less than or equal to 4 is this number. Okay, this comes up common when we start answering questions. All right, but that's just good to get comfortable with that. Let's go to the next example. We have 2 dice. We're going to roll 2 dice. And just to make things a little bit clear, we'll pretend one of the dice is blue and one of the dice is red, even though they could both be white like normal with black dots on them. Let's just make it a blue and a red one. So the possible outcomes when rolling 2 dice The blue dice could be anywhere from 1 to 6. The red dice could be anywhere from 1 to 6. So there's really 36 different combinations that could come out when you roll 2 dice. Doesn't matter what the colors of the dice are, there's 36 combinations that could come out. And those combinations have a total score of the blue dice plus the red dice. So if they both came out ones, the total would be 2. So now the question is, what is the probability? What are the possible outcomes when rolling 2 dice? Well, the lowest possible number you could get is 2. Can't get a 1 because there's 2 dice rolling and they have to at least add up to, have to have a value of 1 or more. So we can get a number as low as 2, and it could go as high as a 6 and a 6. It could go as high as 12. So the possible outcomes for rolling 2 dice, and die is plural for dice, 2 die could be anywhere from 2 to 12. Okay. So now the question is, out of the 36 possible ways to roll 2 dice, what are the probabilities of getting these individual outcomes, 2 through 12? Well, assuming once again, there's nothing wrong with the dice, they each have an equal chance of coming 1, 2, 3, 4, 5, or 6. Then there's 36 equally likely outcomes. A 1 and a 1 adds up to 2. Now, how many ways can we get a 3? There's actually 2 ways that you could get a 3. The blue dice could be a 1 and the red dice is a 2. That would add up to 3. And another way it works is if the blue dice is a 2 and the red dice is 1, it also adds up to 3. So there's 2 ways to get a 3. And that's the reason I said, let's have a blue dice and a red dice. If they were both white, you might miss the point that there's 2 ways to get a 3. Dice on the left, dice on the right, red one, blue one, it doesn't matter. Just some way to make them distinctive. There's several ways to get a 4. We could have the blue dice as a 3 and the red dice is a 1. The blue dice is a 2 and the red dice is a 2. The blue dice is a 1 and the red dice is a 3. That would also add up to 4. There's 3 different ways to get a 4. So now what we want to do is we want to take this entire 36. So first of all, calculating these numbers, we have a formula. So it's the outcome of each dice gets added together, fills out all 36 of these squares. Now we want to say for outcomes, how many outcomes are there? So we can have a formula here, and we could use the count if formula. So we're taking these 36 boxes and we're saying count it if the value is equal to J4, which is the number 2. That's this value. So it's basically saying go through these 36 boxes and count up all the ones that have a 2 in it, which is really this. Okay, now this formula is saying go through these 36 boxes and count up every box that has a 3 in it, and it'll count up 2 of them. Okay, and then if we make absolute values, putting these dollar signs in front, we can copy this formula all the way through this range. So now we know how many outcomes have this particular value. Okay, now we could easily do the probability of each of the values. That's very simple. We just say the outcome, how many particular outcomes there are, divided by the count. Count up how many of these boxes have a number in it, have some value in it that's not blank, and that'll come out to be 36. So the probability of getting a 2 is equal to 1 outcome divided by 36, 1 out of 36. And that's what this number is, 2.78. That's 1 out of 36. The probability of getting a 3, there's 2 of those. So it's K5 divided by 36. So it's this number 2 divided by count how many of these 36 boxes are not blank. 36 of them, of course. Okay. Okay, and then same thing for all of these. So again, this formula just now copies down through here. So here's the probability of getting any particular number. The probability of getting a 7, which is the most likely number, especially if you're a craps player, you need to know that, is 1 out of 6, which kind of makes sense. The blue dice, you let it roll, it could be any number. There's always one roll on the red dice that will make it total 7. If the blue dice is a 5, the red dice needs to be a 2. If the blue dice is a 1, the red dice needs to be a 6. There's always a 1 out of 6 chance you make a 7. Once again, the cumulative distribution function is simply the probability that you will roll a particular number. The cumulative distribution for 5 is the probability that I will roll a 5 or less. Not the probability. This is the probability of getting a 5. This is the probability of getting a 5 or less. 5 or 4 or 3 or 2 is 27.78%. So once again, the probability of getting a 12 should be 1 out of 36. There's only one 12 on this whole grid. There's only one 12 here. So the probability of getting a 12 is 1 out of 36. But the probability of getting a 12 or less is 100%. I have to get a 12 or less. It's 2 dice. I have to get 112 or less. So once again, this one, the cumulative distribution function for the final number, the highest number, should always be 100%. Also, if we added up all the probabilities of all the possible outcomes, that should also equal 100%. So we sum up those, that adds up to 100. And then this one is the probability of all of these added together. So that's just like this 100% and this 100%, that's a sanity check for us. Okay, so that's 1 dice, 2 dice. Let's start flipping some coins. So now at this point, we realize there's just different events that we're dealing with. It could be flipping coins, it could be flipping rolling dice, and we're just counting up how many successes we have. Okay, so if we were to flip 3 coins, and the coin, let's say once again, the coin has a 50% chance of coming up heads, 50% chance of coming up tails. How many possible outcomes are there? Well, if there's nothing wrong with the coins, they each have a 50% chance, then the possibilities are, I basically just enumerated them here. So it could come out heads, heads, heads. You know, first coin, second coin, third coin. If it helps you, think of them as different colors, a red coin, a blue coin, and a green coin. So the coins could come out heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, tail, tail, heads, tail, tail, tail. Now let's decide, because we want to calculate successes and fails. Let's just say, for example, rolling a heads is a success and a tails is a fail. All right, so how many heads do we have, or how many successes do we have? So if the 3 coins came out heads, 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 it would be 3 heads. If it came out heads, heads, tails, that's 2 heads. So this is the number of heads that we have. And I could say count if, go through the whole range and count up how many times I see the word heads. So this function just calculates how many heads there are. Now I'm over here consolidating the data. And I realize, so this is what you have to do as a data scientist. You have to take the application, flipping coins and counting up heads, and now consolidate it into the possible outcomes. So we could have 0 heads, we could have 1 head, we could have 2 heads, or we could have 3 heads. There's no way to have 4 heads. You're only flipping 3 coins. So once again, we have to just figure out how many chances there are of all the outcomes, and we're assuming all the outcomes have an equal chance as each other. So the chances are going to be, I'm going to count up all the times I see 0 in this range. And that happens 1 time. For this formula, I'm going to count all of these heads. I'm going to say, how many times do I see the number 1? I see it here. Uh-oh. Just move my formula. All right. So I see it here, here, and here. I see it 3 times. So this COUNTIF will count up 3 of them. So there's a 37.5% chance I'm going to get one head. Two heads also has a 37% chance. There's three ways to get two heads, 1, 2, and 3. And then there's only one way to get three heads. This one, the first one. Okay. So once again, the probability distribution function for zero heads is 1 out of 8. Right? That's what 12.5% is. The probability that I get exactly one head is 37.5%, which is 3 out of 8. Probability I get two heads, 3 out of 8. Probability I get three heads, 1 out of 8. The cumulative distribution function, the probability that I get so many heads or less, probability that I get 0 heads or less is this number. So the first two, these numbers should always match. The probability that I get one head or less would be 50%. There's a 37.5% I'm going to get one head, plus a 12.5% chance I'll get 0 heads. So there's a 50% chance I'm going to get one or less. There's an 87.5% chance I'm going to get 2 or less, 2 or 1 or 0. So basically these three numbers added up should be 87.5%. And then the probability that I get a 3 heads or less has to be 100%. Otherwise, I did something wrong with my Excel spreadsheet. The probability that I will flip 3 coins and get 3 heads or less got to be 100%. And the probability that some result comes out has to be 100%. Okay, so now this adds an interesting question. What is the probability that the outcome is between 1 and 2? Right, so what is the probability that I am 1 or 2, and including less than or equal to 1 or 2? Now, here's where, for the first time, this cumulative distribution comes into play. If I wanted to know what is the probability that I have between 1 and 2, I could ask that another way. I could say, well, what is the probability that I have less than 3, but more than 0? Less than 3, but more than 0. So the probability that I have 2 or less is 87.5, but the probability that I have 0 or less is 12.5. So I would actually subtract, I take 87.5, and I would subtract 12.5, which would give me 75% chance. So there's a 75% chance that I am between 1 and 2. So that's where I could take this number and subtract off this number and calculate ranges. So now for the first time, the cumulative distribution function is having some use. Okay. What if we decided that instead of doing 3 flips, we wanted to do 10 flips, not 3? Okay. Well, this chart right here that actually has 8 rows in it, there's actually 8 rows in this. The reason there's 8 rows is every time you flip a coin, you double the number of rows you had before. So we flipped 1 coin, and that could either be heads or tails. We flipped a second coin, and that could be heads or tails multiplied against the first one being heads or tails. So that has a 4 rows to a table. Flip 2 coins, you're going to have 4 rows. It's going to be like these 4 rows. When you flip 3 coins, it doubles that 4 to 8. So if we decided to do 10 flips instead of 3 flips, this table, instead of having 8 rows, would have 2 times 2 times 2 times 2, 10 times, which is 1,024 rows. This would have 1,024 rows to it. You could do it in Excel. Excel spreadsheets are very large. We could do it, but it would be tedious to type heads, 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 tails, heads, 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 tails, heads, heads, heads. It would take a really long time to do this. This consolidated chart would count 0 through 10. So this table would about triple in size. but this one would become enormous. So that would be difficult to do. The other thing is we're using this Excel spreadsheet. We're saying heads, 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 tails. And then we're saying, all right, there's 8 possible outcomes. But what if heads and tails are not equally as likely as each other? Suppose there's something wrong with the coin and heads comes up 55% of the time. Then this whole design doesn't work. We would need something much, much better. And in real life, these questions do come up. So this introduces the binomial distribution function. There's a formula for it. Maybe you've seen this factorial notation before, but here's basically the way this formula works. You have an event like flipping a coin, and it's either heads or tails, or even simpler, we could say it's either successful or fails. You have an event, you run the event a certain amount of times, and you're counting up how many times you had a success. You could flip a coin and count up how many times you had a head if you want. Okay. So suppose, for example, you want to know the probability of getting a head is 50%. Okay. What is the probability that if you flip the coin 3 times, what is the probability that you would get 0 heads? Well, we know the answer to this because we did it. It should be 12.5. So let's see, we go to binomial distribution, and we have 0 heads out of 3 flips. What's the value? Well, there's a binomial distribution. So binomial, bi means 2, nomial means numbers, 2 numbers. So we're flipping the coin 3 times and we're counting up how many heads. So we need a function that has 3 and 0 as a parameter. So in Excel, we have a function called the binom.dist, which is short for binomial distribution. And we're going to put in the number S, how many successes we have, and we're going to put in the number of trials, and then we're going to put in the probability that we get a success. So we're going to put in 0 successes, 0 heads out of 3 tries, and the probability is 50%. Now, if you are interested in the cumulative distribution, which is where, the probability that we get 0 or less versus the probability of getting exactly 0, you would put true for this last parameter. Otherwise, if you don't want the cumulative distribution, you would put false. So let me just go over, we did this before. We said, here's the probability, 50% is the probability of getting a 3 or less. I'm accumulating all the probabilities from 0 all the way up to 3. Here, I'm just calculating the probability of getting exactly a 3. This is 3 or less. So that's what this is. If you say false here, you're really looking at this column. And if you say true, you're looking at this column. That's all the difference between the true and the falses. Okay, so suppose so we know this one came out 12.5, and the cumulative distribution was 12.5. We actually manually did it right here, 12.5, 12.5, right? Did that one before. So now suppose we said we're going to flip the coin 3 times and say, what's the probability of getting 2 heads? We did this one before. 2 heads out of 3, 37% chance. You're going to get 2 heads out of 3 flips, and an 87.5% chance that you will get 2 or less. So if we go to the binomial distribution, we plug in binomial distribution, we say false, we get 37.5. Same formula with a true. That's the cumulative distribution. We get 87.5. So really, this function's doing all of this, laying out all the stuff and counting them all up and all the count diffs to build these charts. It's doing it all for us. So it's a great function. Here's where it would take us forever doing this. And here we just get the thing done, bang it out in a second. So if you flip the coin 7 times, what's the chance of getting 4 heads? I put a 4 here, a 7 here, so I could start cranking out my formulas. And I get the probability function with a false. And then I get the cumulative distribution by putting in a true. So the probability, if I flip the coin 7 times and the coin is a 50% chance of being a success, being heads, the probability of getting exactly 4 out of 7 is 27.34. The probability of getting 4 or less, meaning 4 or 3 or 2 or 1 or 0, is 77.34. This one's a little surprising. The probability of getting 8 heads out of 10. This looks about intuitively correct. This one I thought was a little bit high, but to get 8 or less is a 98, almost 99% chance you're going to get 8 or less. Very low chance of getting 9 or 10 heads. So, okay. And now suppose we wanted to, and this just goes into modeling a series of events. So suppose we wanted to model the World Series, Baseball World Series. So it's a 7-game series. First team to get to 4 games wins the series. The series starts off with a score of 0-0. After the first game, you could either be winning the series 1-0 if you win the first game, or you could lose the first game and you're losing the series 0-1. So now after the second game, what are the possible outcomes? Well, you could start off the series at 0-0, win the first game, and win the second game. Now you're 2-1. You're winning the series 2-1. I'm sorry, 2-0. You could win the first game and lose the second game, which means the series is tied at 1-1. You could also lose the first game and win the second game, which means the series is also tied at 1-1. And the third case is you could lose the first game and then lose the second game. And now you're losing 2-0. So after 2 games, you could be winning 2-0, 1-1, or 0-2. And then this keeps repeating. So this graph where the points re-merge back together is called a lattice. And if at each point it has 2 possible outcomes, like win or lose, like in the World Series, that's a binomial lattice. Okay, and we can represent, we could try to model or figure out who's going to win the World Series by, again, using Excel. So we create a table, and it shows how many times you've won, 0, 1, 2, 3, or 4. And this is how many times your opponent has won, 0, 1, 2, 3, or 4. And the probability that the series will be with an initial score of 0-0 is 100%. It'll always be that way. Now, here's where we're doing something a little bit interesting. We're saying, suppose the probability of your team winning a particular game, let's say your team is not quite as good as the other team, slightly worse. So the probability that your team's going to win an individual game is a 45% chance, not a 50% chance. Okay, so we'll put that in here. Now the probability after 1 game, you're winning 1-0, 1 win for you, 0 wins for your opponent, is the previous. So it's really this value times 45% chance will get you to here. After 1 game, there's a 45% chance your team will win the game. And there's a 55% chance you'll lose the game and your opponent will be winning 1-0. 45% chance you'll be winning 1-0. Okay. So now, what is the probability that you will start off at 0-0, win the first game, and win the second game? Well, that's the probability. You start off at 0-0, which is 100%. You win the first game, which has a 45% chance of happening. And then you win the second game, which has a 45% chance of winning the second game after a 45% chance of winning the first game. So this is the probability that you'll win the first two games, 20.25. Probability you win the third game and fourth game, then you shut the team out 4-0 is 4% chance. Of all the other combinations, now this one is really this box right here shows up right here on the lattice. That's the probability that you either win the first game and lose the second one, or lose the first one and win the second one. Either way, the series is tied at 1-1. So this box represents, this 49.5 represents that the score is 1-1 after two games. So you can easily construct each one of these boxes by just saying, what is the probability that the box above me was the score of the series right before this game, and then the probability that the result I'm looking for happens, plus, see, so the probability of the probability that I won the first game and lost the second one, plus the probability that I lost the first game and won the second one, and I add it up. And now I just spread these formulas throughout the whole box. Now, here's the thing, when you're an application data scientist, there's something a little bit wrong with this box. And this is where you have to know your application. You have to know how the World Series works to know that some of these numbers are not calculated right. This box right here represents the series getting to a score of 4-4. But that could never happen in the World Series. And it's basically saying there's two ways I could get there. I could get to 4-3 and then lose the next game, and I could get to a score of 3-4 and win the next game. But if the series was 4-3 or 3-4, there wouldn't be a next game. So this box shouldn't even have any value in it at all. The other boxes, this box right here, we added the probability of winning the series 4-0 and then losing a game, plus winning the series 3-1 and winning a game. But if you're winning the series 4-0, you can't then lose the next game. The series is over. So all of these ones in highlights, I had to go and manually adjust them simply to the rules of baseball. And so I marked those in red. So that's you being the data scientist, not just, Excel just blindly copies formulas, but then you have to adjust your application. So it's kind of interesting. So if let's say two teams are playing each other and they each have a 50-50 chance of winning an individual game, then the probability, of course, and it makes sense, you'd have a 50-50 shot of winning the series. But if one team is a little bit worse than the other one, let's say they play each other in an individual game, and the team that's a little bit worse has a 45% chance of winning each individual game, then you might ask yourself, what's the probability that they could win the whole series? And that's even less than 45%. It's 30, it's down here. Let me just highlight that. So it's 39.5%. If your team only wins 33% of the time when they play a game, then you have like a 16% chance of winning the series. So a series will accentuate a bad team. And that's kind of what we're showing here. Okay, so yeah, so here what we're doing is we're modeling, we're basically modeling the behavior of the World Series, and then adding a little data science to it just to show that, we don't want to blindly follow what Excel's formulas do. We have to tailor it to the application.